Okay, well, thank you to the AWSMP for having Jillian and myself here today. Um, it might be a little odd to see two different consulting firms co-presenting on the subject, but Jillian and I have worked together on a number of projects in the Ashokan Watershed over the years, including multiple stream restoration projects and the Mink Hollow bridge replacement that focus on incorporating stream process into design decisions. And we'll share a little bit more on Mink Hollow later on in the presentation. Okay, that's for an agenda. We'll do a brief introduction of the topic. Then we're going to talk briefly about watershed and site assessment. We'll go into some problem definition and design goals, as well as some design best practices. And then we'll touch on construction considerations and then post-construction monitoring and maintenance. And we'll also focus on two case studies located in the Ashokan Watershed, the Mink Hollow Bridge Replacement Project, as well as the Upper Boiceville Culvert Replacement Project. Okay, so introduction. Why do bridges and culverts fail? Oftentimes it can be associated with structural decay or undersized and crossings that are inadequate for current conditions. There may be poorly designed, so there could be a weird skew to the stream center line. They might be limited by site constraints. And then there's other factors that are a result of the rivers that they cross, including sediment dynamics. So things like scour, deposition, debris plugging of the hydraulic opening, and then just having to contend with extreme hydrology. So why consider geomorphic compatibility and why does that matter? Um, and really the main kind of focus and I think takeaway from this presentation is that by including geomorphic compatibility in road stream crossing design, you can really help extend the structural lifespan of a cross or reach the structural lifespan of a crossing so that you don't see premature failure. And it also helps reduce costs associated with if that crossing fails prematurely or repeat maintenance needs. And so why does the Ashokan Watershed Stream Management Program go above and beyond? Well, really the goal is to increase project lifespan, delay future maintenance and replacement costs that are financed by taxpayers, protect water quality for drinking, but also local water users, including recreationists and fishery folks, and an economic boost to local economy. So we know that clean wild rivers are one of the region's draws in the Catskills, and the Upper Soapus Creek in particular was recently designated a wild trout fishery. So the focus here in integrating the geomorphic conditions in road stream crossing design is really to have a crossing that works with the river and not against it. We're going to introduce some of the assessment methods, review best practice, design principles, and then demonstrate integration of those principles into roadway infrastructure design. So we wanted to touch on a couple of examples that are relatively local to the region. One is kind of this infamous Schoharie Creek Bridge failure on New York State Thruway or I-90. And this was a result of an April 5th, 1987 rain on snow event that equated to approximately the 50-year flood. It was a result of kind of design decisions that didn't consider the potential for this bridge to scour. It was designed with reinforced spread footings, which were relatively shallow, and then those were just protected by a dry layer of riprap. So during these flood conditions, that riprap was removed, the footings undermined, and we saw 3 spans collapse into the Schoharie Creek. Another more local example, as a result of Tropical Storm Irene, is Alpine Road Crossing in Big Indian, New York, or Oliveria. And as you can see here, this was a different type of failure. You can see, let me see if I can pull up a pointer. Or can you at least see my pointer, Max? Okay. So you can kind of see what happened here. You can start to see a little bit of it right here, but this culvert was hydraulically inadequate for both the floodwaters that were delivered that day, but also the debris that was coming from upstream. And so the culvert itself had clogged, leading to the stream to actually shift and avulse through the roadway approach here. And if you look kind of closely upstream, there's a couple of things that we see that might indicate that the crossing was not considering the geomorphology of the stream at the time of its construction. So you see that we have a little bit more floodplain access evident by the low bank height on the upstream. And when you get down into the culvert crossing location, you can see that it was a much more entrenched or vertically contained channel. So now we're taking these waters that were able to spread out onto the upstream floodplain and condensing them all down to this vertically contained channel and trying to force them through this arch culvert design. Once that plugged with debris, since it couldn't adequately convey the wooden material that was coming downstream, it led to this kind of drastic failure and avulsion where the stream just cut directly around the culvert. A lot of the sites in the Catskills get complicated by the geology of the Catskills. So you can see in this picture, this right bank here, looking upstream, the presence of some lacustrine deposits that were linked to the last ice age. So when that material, which is typically overridden by alluvial sediment, so the boulders and the cobble, it oftentimes leads to a very quick unraveling of the stream channel and incision process that leads to that drop in bed elevation. Okay, so moving a little bit towards watershed and site assessment to set you up for considering geomorphology and road stream crossing design. So you really want to start at a watershed scale context. So start to look at and understand the hydrology and factors influencing how water is delivered to the road stream crossing. In terms of aquatic connectivity, you're not looking at just the crossing, but potentially upstream and downstream as well, so that if there is an aquatic organism passage improvement at the project, are fish actually being able to migrate to there? Is there a natural barrier downstream or even an artificial barrier? And one amount of watershed gets opened up through alleviation of that AOP issue. In terms of sediment transport, oftentimes you're out there doing pebble counts or measuring features within the stream to start to understand the potential for the stream to move sediment. As a lot of you folks know, in the Catskills, these high mountain streams are essentially conveyor belts for sediment. So when considering the geomorphology at a road stream crossing, you really need to take into consideration the fact that it's going to be moving not just water, but also sediment, as well as potentially wood and other debris through that crossing. That leads you to conducting what's called a geomorphic assessment, so starting to understand the pattern, profile, and dimensions of the stream channel through the crossing, but also downstream and upstream to try to mimic the natural stable conditions that you might find above or below the crossing. As Max mentioned, there's also the structural assessment component, so looking at the structural health of a crossing. Max mentioned the MOSCAP protocol that was developed in the Ashokan Stream program, and that does a good job of integrating the DOT's structural condition assessment tool. So all of these kind of components come together to really help create a way to prioritize different crossings and find out where you're going to have the best benefit for the effort. And really the complexity of a given site is what drives the next couple of topics that Jillian's going to touch on. In this instance, we're looking at the De Silva Road crossing. This is Route 28. This is Old Route 28. And this is De Silva Road here. And you can see it's a relatively vertically confined channel. The old Route 28 culvert was actually the limiting factor for and reduced the hydraulic capacity of the newer Route 28 culvert. So this was a site that you instantly look at and start to say, there's some complex things going out. So maybe we need to take an additional look at some of these other characteristics and consider them as we're advancing through design. All right, I'm going to turn it over to Jillian now.
Hey, thanks, Adam. So as Adam just touched on a bunch there are certain environments that pose additional risks to the long-term function of a stream crossing. And in these situations, it's important to consult with a geomorphologist to ensure that the design is incorporating these channel conditions. So as we saw with Alpine Road, when you have a steep, high energy channel like Elk Bushkill in that situation, you have a lot of energy trapped within the channel, and that can lead to bed erosion and bank erosion around the structure and can undercut elements of the structure. There's also typically a lot of sediment and debris movement in these systems, which can clog and reduce the capacity of the structure, as seen in the Alpine Road. And then even in flatter systems, when there's a lot of sediment and debris movement, there's also a higher potential for that material to reduce the capacity of the structure. And a good way to tell if that's a concern for your site is if there's evidence of channel aggradation. So if you're seeing mid-channel bars or side channel bars, woody debris aggradation, those are all things that would indicate a high sediment load and or inadequate sediment transport through the reach. Okay, next slide, Adam. Incised or entrenched channels also pose a higher risk to crossing structures. So an incised or entrenched channel, even at flatter slopes, can contain a lot of energy and sediment movement due to the lack of connection to the floodplain. Basically, water during flood flows can't spread out, it's trapped in the channel and it can't dissipate energy. So in extreme cases like Alpine Road, the channel can completely undermine or cut around the crossing because it doesn't have anywhere else to go. Additionally, channels with wide floodplains, which are typically lower energy channels, but it's not usually cost effective or feasible in some cases to span the entire floodplain. So the structure can cause a drastic constriction of flow, and that flow constriction can impact the continuity of stream flow in the stream channel, as well as create erosive forces near and around the structure. It also can cause backwater as that flow constricts and slows down, which can cause sediment to drop out upstream of the structure, which can reduce the capacity. So these are some scenarios where it would be important. There's a little bit more complexity going on. It would be important to consult with a stream professional and evaluate the geomorphology of the channel and really understand how to adequately incorporate these dynamics into the overall design. So if you've identified that you have a site where a geomorphologist is needed, these are the elements to evaluate the design from a geomorphic perspective. So first, providing adequate conveyance. That's most important, making sure that the structure can pass the flood flows, ideally without causing backwater, because that can cause impacts to the hydraulics of the structure. And then this also plays into maintaining the upstream and downstream conditions of the stream channel to the greatest extent possible, really in order to minimize the impact to the natural stream function. And then also sediment transport, as Adam touched on, that's a big component of this. Looking at sediment transport and evaluating whether the structure will cause an increase or decrease in existing sediment transport, or if there's already an existing issue, whether there's too much sediment transport and you're seeing bed degradation, or there's not enough and you're seeing aggradation at the structure location. There are ways to incorporate stream structures to promote the stability and address those sediment concerns. It's also important to maintain aquatic organism passage. And a big component of that is using natural substrate, as well as ensuring there's not going to be bed degradation, especially downstream of the structure. If the downstream channel erodes out, it can cause a fish passage barrier at the structure. So these design goals are all aimed at maintaining or if needed, improving stream function at the project site. And really, the more you can maintain natural function, the less long-term maintenance costs they're going to be associated with that structure. And to properly evaluate the geomorphic conditions and the potential impact on the structure, the scope of work for the design should really include, at a minimum, these components shown here. So we start with a geomorphic assessment, and that's completed in the field where we take measurements of the channel. We look at the existing cross sections, the slope, identify areas of erosion or aggradation, know any woody debris, or debris accumulation, and this helps inform the existing conditions and parameters of the stream channel and identifies any areas of concern. Next, we would do a hydrologic analysis, which is needed for any structure design, regardless of the geomorphology, to ensure the proper sizing of that structure. However, from a geomorphic perspective, the hydrologic assessment will also estimate the bank flow discharge and base flow. So looking at some of those lower flows in addition to the higher peak flows as well. And that's really to evaluate typical flow conditions, which informs channel sizing and sediment transport. And then hydraulic modeling, which is also typically necessary for crossing design. And the geomorphic component would focus on the lower flows as well as the flood flows and those peak flows to evaluate the range of velocities and shear stress and other hydraulic parameters that the crossing will be subjected to. There's also situations where it's really valuable to do two-dimensional modeling instead of the standard 1D. Two-dimensional modeling allows a much more detailed depiction of flow dynamics, as well as discrete changes in velocity. It also better defines out-of-channel flow. So if there's a large floodplain area or there's a lot of complexity in the site, a 2D model will definitely provide better results. And then finally, sediment transport is one that can typically be missed, but is very important to the structural integrity. And depending on how complex the site is and what data is available, this can be done from a more qualitative perspective, all the way up to a very detailed model can be completed to analyze the sediment transport through the reach and the crossing. And then we'll talk about some design best practices. So starting off with just the basic sizing and geometry requirements for bridges. This is from the New York State Bridge Manual. So bridges should be designed to pass the 100-year discharge without touching the low chord. And then at the 50-year discharge event, there should be a minimum of 2 feet from the water surface elevation to the low chord of the bridge. The alignment of the structure ideally is perpendicular to the channel, but it can be placed up to a 10-degree skew if needed based on site conditions. And all disturbed banks need to be protected up to at least 1 foot above the high water elevation. And the span requirement for the bridge manual is based on capacity and required structure depth, but should really incorporate the floodplain to the greatest extent feasible, which is often limited by cost. But the DEC recommends at least 1.2 times the bankable width or the average channel width. And when looking at materials and structural considerations, using natural bed material whenever possible, really to maintain the stream function and aquatic organism passage. Scour protection around the abutments and wing walls, outlets if it's a culvert, and on the stream banks, both upstream and downstream of the crossing need to be evaluated to protect the channel and the structure. Abutment and pier placement needs to be considered. A single span bridge is preferred, but if piers are needed, ensuring that they're placed far enough apart to not accumulate woody debris and that they're aligned in the direction of the stream channel, both the piers and the abutments, to reduce the impacts on the stream flow. And then additionally, if there is a really wide floodplain, you can use floodplain crossings or culverts to help maintain the continuity of flood flows flowing along that floodplain. And this just discusses a couple different the 2 main categories of types of structure. So bridges and open bottom culverts are the preferred method. These allow for the stream bed continuity and the fish and wildlife passage. They also have a little bit more roughness and reduced velocity. Closed bottom or culverts or pipes, these are typically less expensive and they're used for smaller water flow. But they don't come with some of the benefits that, of the stream bed continuity and fish and wildlife passage. You can, if you're using a pipe, you can oversize it and then partially bury it to get that stream bed material in the pipe as well. So that's something to consider for design if the design does call for a pipe. And then when looking at how to incorporate the geomorphology into the design, we're looking at the existing channel slope, the alignment evaluating shear stresses and velocity using the hydraulic modeling, looking at the floodplain connectivity of the channel and the potential impacts of that on the structure during flood flows, looking at the potential for debris accumulation. Is there a lot of loaded debris in the channel? And then, trying to maintain the existing conditions of the channel as much as possible. So maintaining, the upstream and downstream conditions to the extent feasible. And then some typical in-stream features you can incorporate to help maintain or improve the stream function include having appropriate channel geometry. So having a bankful channel, maybe a low flow channel if sediment transport or deeper water for fish passage is a concern. Vegetation is also an incredibly important factor in any stream design. So vegetation not only improves the riparian and aquatic habitat, but it also drastically improves the stabilization as well. So even if rock is needed for bank stabilization, which around these structures it typically is, vegetation can be incorporated into that rock, and that really helps solidify the structure and reduce erosive forces being applied to the stream banks and to that rock material. Additionally, if bed degradation is a concern, so if there's, a potential for head cutting, grade control upstream and or downstream of the crossing can be installed in conjunction with the crossing. That's what you see here in this picture. There's a series of boulders placed across the width of the channel, and it's placed at grade and then buried, and that's to prevent head cutting as well as kind of to promote indirect flows through the middle of the channel and away from the abutments and the edges of the channel. And then bank protection upstream and downstream of the structure needs to be evaluated and included. So that typically includes rock, it typically requires rock as stated above. But incorporating vegetation is recommended to increase the long-term stability of any rock stabilization features. And then lastly, considering climate resilience. If you're putting in or replacing a bridge, you want to make sure that it's able to function for its lifespan. So with changing weather conditions, designing structures for future predicted hydrologic conditions will help improve the long-term stability and function. So the structure should be sized, if feasible, to the future peak flows, which can be specified in the scope of work. And then for New York, Cornell has published future projections of intensity, duration, and frequency curves, which can be used to calculate those peak flows, the future peak flows. Moving on to some considerations or things to consider during construction. So installation of bridges and culvert structures should be installed in the dry to reduce the effects of turbidity. An approved dewatering plan should be included with the design. This typically includes piping flow around the work site, usually through pumping. The flow downstream should be the same as the flow upstream so that you're able to maintain that continuity of flow. The duration of the dewatering should be kept to a minimum to limit impacts to the stream. And then if the project site is large or complex, staging construction may be required or beneficial just to limit the amount of open or exposed work areas that are occurring at one time. And when reviewing access and dewatering plans, need to make sure that habitat and resources are protected. So this can be done by minimizing the overall site disturbance as much as possible. So only utilizing and disturbing the area that you need to construct the design. Utilizing open areas to avoid any tree impacts, and then avoiding any wetland areas. If you do need to cross the wetland area, that needs to be done in a way to protect that resource. So using something like timber matting or something that won't disturb the wetland areas, if that's required. The construction will also need to be scheduled around stream closure periods. And then if there are rare or endangered species like that's located near the project site, then there will be additional time restrictions that will likely be required, and all of those should be noted in the permitting documents. And then finally, during construction of the in-stream features, a qualified inspector should be on site to observe installation. A lot of times contractors are not familiar with the proposed structures that are put in the stream, especially if, they're a bridge contractor. And proper installation of these structures is definitely necessary for long-term stability and to ensure that they function as intended. Additionally, downstream areas should be monitored for excess sediment releases. So if the water coming from the project site is muddy or less clear than it is upstream, then the dewatering and erosion sediment control devices should be checked and repaired or modified as needed. And with that, I'm going to turn it back over to Adam to talk about the post-construction monitoring and maintenance.
Thanks. So I'm going to run through a couple of slides showing some examples of what to kind of look for post-construction. So this is after you've had your road stream crossing improvement project, and now what to watch for over the next coming months and years. And it's really kind of going to focus on three different areas. So the vegetation, potential channel response to the alterations of the stream, and then the structural components. So vegetation, absolutely critical for long-term bank stability, as Jillian mentioned earlier. The complication with it is that it often takes a long time to fully establish. And so that means that it may require repeat monitoring and maintenance. One of the best ways to monitor a site, if you're not going to do a detailed assessment of the vegetation, is really just through photo monitoring. So that could be as simple as taking your phone out of your pocket and taking pictures periodically. And then oftentimes the projects, there's going to be an initial warranty of the live materials that are used, whether live stakes like in this picture or potted material. So getting out and inspecting it before the term expires of that warranty, so that you can bring the construction contractor back to replant if needed. A word of caution when monitoring willows, oftentimes they're installed in the dormancy during the fall or winter even, and they have a metabolic reserve in them, so they'll typically sprout out the next year if they haven't desiccated or had any other issues, which can kind of make it look initially like everything's doing really well, but then you can see mortality going forward as the root network doesn't fully develop. So it's good to check on them beyond necessarily that first year post installation. Next, we'll focus a little bit on channel responses. So one potential thing to look for would be any incision or head cutting. So incision is just a change in the vertical placement of the stream bed. Head cutting is a term for this drop in bed elevation that tends to propagate upstream, and you can kind of see an example of that here in this photo. If you look upstream, you can see the bank height kind of gradually increases as you come downstream. And so this is another example where the stream had incised into these glacial legacy sediments and then arrested at this kind of boulder structure up here, which is a natural boulder step. So you're kind of looking at changes in potential bank height or adjustments to the stream bed. It's really important to kind of evaluate the transition points. So anywhere you've got the undisturbed stream coming into the project site or then going downstream to where the project work ended. Those can oftentimes be areas that might be more prone to adjustment because of the attempt to tie into this from this constructed channel to the natural conditions above or below a project. Another good way to kind of track this would be just through simple things like photo monitoring. But also if you're really interested in potential changes in elevation to the bed or adjustments such as head cutting, then conducting longitudinal profile surveys or monumented cross-section surveys allow you to track it over time. Another potential channel response related to the sediment transport side of the geomorphic assessment would be any aggradation or sediment buildup. So post-construction, are you seeing bar formation, either development upstream or downstream or through the structure, or just changes in how the sediment is moving through the project reach? Um, Jillian had mentioned that it's typically best practice to span the entire channel in those situations where you are going to have pier in the active channel. That can oftentimes lead to not just accumulation or trapping of like wood and other debris, but also sediment. So important to look at how those bars might develop over time. And then really, when you're going through the construction phase of the project, you're disrupting all of this naturally placed alluvial material, and that can oftentimes lead to a more higher volume sediment moving downstream just post-construction because it hasn't had a chance to imbricate or reform the armor layer. Um, so really evaluating whether or not the hydraulic capacity of the new crossing has been impacted by sediment deposition and maybe repeat monitoring over a course of higher flows to see if that sediment is kind of flushing through and starting to reform that armor layer, or if you potentially have an issue that might trigger management intervention. Another potential channel response condition to be aware of is just to evaluate each of the in-stream features that were included in a design and evaluate whether those features are performing their intended purpose. So in this instance, you're looking at kind of a step pool morphology, and these larger rocks are used to hold that grade. So these are going to be immobile under the design flow, but still allow sediment to move through the site. So have you seen where maybe footer rocks that would be below the water surface have undermined as a result of a scour pool forming? Has that compromised the integrity of that cross structure, cross vein or boulder weir or step pool feature? Um, and then in other instances, you might have overly steepened section through the use of a in-stream structure to help with the sediment transport condition. And so evaluating whether or not that is leading to the intended design. We already mentioned it and demonstrate the issue with potentially having large wood accumulation on bridges and culverts. So one way to consider this is to actually evaluate it during the design so you can model a blockage, a certain percentage of the hydraulic opening being blocked or obstructed, and what are the impacts of that in terms of whether the infrastructure is overtopped or the low chord's impacted. And then oftentimes you're really going to need to work with the owner for removal. So that might be local Department of Public Works or highway managers within the local community to come up with a plan to remove it so that you can restore that hydraulic opening. And really, the large wood accumulation might not even be a function of the project that was recently been completed there. There's a tremendous amount of wood upstream in these um, highly forested areas of the Catskills. So it's a natural process for the wood to move down channel, and keeping an eye periodically over after a higher flow events is a good way to just check on the road stream crossing network and make sure there isn't a potential issue there. I'm not as qualified to talk about structural components, but some things to just keep in mind is settling of compacted fill. You can see an example of that here where the fill in a void space that was probably left as a result of some of the riprap used started to wash the finer topsoil down. So evaluating that because a potential hazard if somebody out there inspecting the bridge or even recreators trying to access the river at that location. You don't want a trip and fall hazard. Evaluating the structural integrity of wing walls, footings, abutments, etc. Inspecting for cracks or anything that may indicate that there's some irregular wear post-project. A good place to double check too is pavement. So the over pavement on the top of the crossing, are you seeing settling or cracking, indicating that there's some type of settling going on? Max covered this earlier, but who can help? So for those in the Catskills and the West Hudson Watershed, you can consult with your local stream management program, who may be able to help set up a monitoring plan for a particular project, especially if it's one that they've been involved in implementing. There's obviously the owner of the bridge or culvert, so local, county, or state entities that can either perform the structural inspections or additional inspections and create documentation for having completed the monitoring. And then one consideration to even think about when you're back in the design process is really building adjustment thresholds into the project goals and design. So that's creating metrics that once met might trigger a management intervention. And it can be useful to consider that, at the start of the project versus after it's been constructed in. Okay, so now we're going to focus on two local case studies. Jillian's going to talk first about the Mink Hollow Bridge replacement.
Okay, so this was, yeah, a bridge replacement that was completed on Mink Hollow Road over Beaver Kill. This is existing condition, so you can see it's a single span bridge. Span length, the existing span length is 55 feet, which had a capacity to convey the 25-year event. Along the left bank, you can't see it as well in this photo, but there's extensive bank erosion that was threatening a residential structure on the top of the bank. There's also some erosion occurring downstream as well. And then there's some aggradation occurring along the right, and this is also a relatively steep section of Beaver Kill. So considering sediment transport, there was a lot of woody debris located upstream, and considering sediment transport through the bridge as well as potential for bed degradation. So, the project scope, the goals for the project were to improve the hydraulic capacity of the bridge to the greatest extent possible, as well as maintaining the geomorphic function and aquatic organism passage. The project approach included doing a geomorphic assessment. So we did you can see here in this picture, we have table across here. We did several cross sections upstream and downstream of the bridge. We did the longitudinal profile. We took pebble counts, lots of photo documentation. We also did the hydrologic analysis and determined appropriate channel sizing. And then a sediment transport analysis and a hydraulic analysis as well, which I believe we did a 2D model for this project. And then this is the completed structure. So it was completed, construction was completed in 2021. We replaced it with another single span bridge that increased the span length from 55 feet to 80 feet. And we're able to convey the 50-year storm instead of the 25-year storm. And then for bank protection along the left bank in this picture, and then on the right bank downstream of the bridge, we have some large riprap material that was interplanted with live stakes, which you can see are doing pretty well here. After establishment, we also included a rock sill, so a channel spanning structure, which included some large boulders sized to be stable during the high flow events as well. And that was really to aid in sediment transport during the lower flow events, as well as provide some energy dissipation and grade control during the higher flow events. And I will pass it back over to Adam to talk about the Upper Boiceville Road culvert replacement.
Thanks. Okay, so the Upper Boiceville Road culvert replacement project was actually identified during one of the local flood analysis that was completed for the community of Boiceville. It's shown here as a steel beam deck atop concrete abutments. It had a span length of only 7 feet, and you can kind of see on each of the approaches, it really kind of pinches down on the channel. So it was definitely identified as a hydraulic constriction. The capacity of the previous structure was 25-year, and the stream kind of features this high gradient, so greater than 5% slope, kind of step pool morphology. In terms of the project goals, improve hydraulic capacity for this constriction, maintain the geomorphic function. So really wanting to mimic the bed form that was present both upstream and downstream of this crossing. Improve aquatic organism passage. So this crossing is over an unnamed tributary directly to the Ashokan Reservoir. It's known and interacted with some of the local trout unlimited folks that it's a good potential for spawning habitat upstream. And there was no other really significant barriers downstream other than the DeSilva Road crossing, which I'd mentioned briefly earlier. So this project was constructed in coordination and at the same time or right after the DeSilva Road crossing. So we wanted to evaluate predicted future flows as well for this one. And the approach utilized geomorphic assessment, subsurface exploration, um, hydrologic and hydraulic analysis, and sediment transport analysis. And you can kind of see the really importance of the subsurface exploration because it's another example where you have those glacial legacy sediments overridden by a shallow alluvial layer, and could present potential problems depending on what type of structure was chosen for this location. Oh, sorry, I wanted to mention one other thing. So in terms of evaluating the aquatic organism passage, we conducted modeling to look at spring spawning high passage flow, as well as fall spawning high passage flow, and then low passage design flow. So that was just to try to hit the key components of trout life history, so that they, can get upstream and through this crossing during their preferred spawning period, spring versus fall, as well as what the conditions through the new crossing would be under lower flow conditions during the summer, and still being able to maintain an adequate depth of flow so that they can pass through this crossing. So this is the completed project. It's a four-sided box. So again, going back to that glacial legacy sediment and geology there, the decision was made to use a four-sided box to help aid with grade control protection, despite utilizing two in-stream structures as well. There's a step kind of pull feature on the upstream and downstream portion that kind of mimics the morphology that was seen in that higher gradient channel. But Jillian had alluded to earlier, you can often oversize the height so that you can incorporate natural sediment here. So that was an important component. So it's actually a 7-foot effective opening, but it's a much larger culvert height, and it's buried with a couple feet of natural sediment to mimic the conditions upstream and downstream, and also give us an opportunity to kind of carve that low flow channel that was critical for summertime flows. The new crossing can actually handle the 50-year future, and that is included with a 20% potential blockage. So that was one of the alternatives that was evaluated through the design process. So there's a little additional hydraulic capacity beyond just the 50-year future. Again, step pool, grade controls incorporated in the aquatic organism passage low flow channel. I think we're getting close on time, so maybe we'll wrap that up and then open it up to a couple of questions. So in summary, resilient road stream crossings, they're not just good for the stream, but they're good for the crossing. The geomorphic compatibility reduces the long-term failure risk as well as minimizing maintenance costs. Road crossings work with the watershed process, not against it, so it's good for the stream. It's also good for the dollar and good for the fish. Investment in geomorphically sound design reduces long-term costs and increases ecological connectivity. So you might have a little bit more upfront costs through the assessment and design components, but hopefully that structure will live to its full structural lifespan with limited maintenance needs. And it's also good for the communities. So, the Mink Hollow Bridge and the Upper Boiceville Bridge, in Mink Hollow instance, that's the only way in and out of this kind of hollow up there off of the Beaver Kill. So it's critical that that crossing remains open for the homes that are above it. And with the Upper Boiceville Road crossing, during times that the Esopus is a significant flood stage and Route 28 is impassable, it becomes the critical route out of Boiceville and allows that community to provide essential services and flood recovery response. So Brazilian road stream crossings are good for the community. They protect critical travel corridors from extreme hydrology. They responsibly use taxpayer funds and just make for more resilient communities. This is a little AI generated photo of trout going upstream, but also the dollars going upstream. So not throwing your dollars away with kind of outdated design approaches. And I think with that, we will open it up to any Q&A.